All right, so what is this resonance thing? Well, we're going to talk about the nitrate anion, and this is actually a good example because I'm going to work through the entire Lewis structure process for it anyway. So nitrate, it's a separate ion by itself, so that was step one. These numbers represent the steps in my handy dandy procedure here. All right, so it is a separate ion, so we don't have to do that. Valence electrons. The nitrogen contributes 5. There are 6 coming in from each of the 3 oxygens, and when you've got ions, add or subtract the appropriate number as a charge. So this is a -1 ion, so it's got 1 extra electron that brings the total up to 24. Let's build the bonding framework. The formula would have you indicate that nitrogen is in the middle and the oxygens are bonded to it. So this. Step 4, put 3 unshared pairs around each outside atom. So there we go. And that is all 24 atoms. So you've got 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Step 5, assign any other electrons to the inside, which we can't because there aren't any. So that's step 5. Next, look at the formal charges. So this is good practice. So I would say hit pause and calculate the formal charge on the oxygen and on the nitrogen. So the nitrogen, it has 3 unshared pairs, 6 electrons. It gets half of those. So we can assign 3 electrons to it in that structure. It normally has 5 valence electrons, giving it a formal charge of +2. The oxygens, it has 6 unshared electrons, one shared pair, so it gets half of those 2, giving it a total of 7 electrons, and they're all the same. And oxygen normally has 6 valence electrons. It has 7 in this structure, giving it a formal charge of -1. And they're all the same. All right. And another little tidbit here that's in the group activity. If you've done things correctly, the formal charges will add up to the overall charge on the thing. So in this case, we have a +2. We have 3 -1s, giving it a total of -1. If that doesn't match the charge, whether it's 0, if it's neutral or whatever, a mistake has been made. So keep an eye out for that. And apparently this has been repeated, so ignore that. Now, next step is to minimize the formal charge, if at all possible. And we do that, again, the same way. So we can take one of these unshared pairs and make it a shared pair. So let's recalculate those formal charges. So these won't change. The formal charge on the oxygen now is 0. So it's got 1, 2, 3, 4, 5, 6. And it usually has 6. And the nitrogen has gone from +2 to +1. You can assign 1, 2, 3, 4 electrons to it. Usually has 5, so it's got a +1 charge. And nitrogen now has a octet, as does oxygen, and actually these oxygens as well. So could we keep on doing this? Could we promote one of these unshared? Could we move one of these unshared pairs to make a shared pair? Make it a double bond. And this creates a problem because now if we were to do this by Lewis counting, this nitrogen atom has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 5 pairs. And that doesn't happen. Again, nitrogen is a second row element. It does not break the octet rule, so you can't do that. So we're back to where we started. So it turns out that the 1 double bond is the best we can do. This leaves residual formal charge on these 3 atoms here, but that's okay because nitrogen, you just can't break the octet rule for nitrogen. So then the next question is, which one? I randomly made this one the double bond because it might have been easiest to draw it that way, but I could have just as easily have done this or done this. Now you'll note that these are all the same structure, they're just rotated by 120 degrees. Each of them contains 1 nitrogen-oxygen double bond and 2 nitrogen-oxygen single bonds. And there's a problem with this, that you can't randomly pick one bond to be different than the other. And we know this is a problem because in real life, nitrate does not look like this. So Einstein didn't like a probabilistic universe. But the idea is that we also know that there's a correlation between a bond being a double bond or a single bond or a triple bond and its length. Single bonds are the shortest. They're the longest. Triple bonds are the shortest and double bonds are in the middle. And we know that, so this one, any of these structures should have 1 nitrogen-oxygen bond that is shorter than the other 2, and we don't see that. Furthermore, what we see is all bonds are exactly the same length, and they are a length that is intermediate in between what you would normally look at for a nitrogen-oxygen single bond and a nitrogen-oxygen double bond. And this represents the big shortcoming of Lewis theory, which assumes that electrons can only be shared between adjacent atoms. And that turns out not to be true. So the way nitrate is held together is that there are 3 pairs of electrons that are localized between the nitrogen and oxygen atoms. But there's 1 pair, so one of these 4 shared pairs, that is actually shared between all 4 atoms of the molecule. And so they are roaming around, occupying space that helps all 4 of these hold together. And the Lewis structure can't show that. So what Lewis structure does, it will show you all 3 possibilities. And the way that you read this is that it is an average of all 3 possibilities. And that gets you to each of these bonds being like a 1 1/3 bond. Now, what you do not want to think about these as the structure is simultaneously changing from this one to this one to this one. If that is occurring, it is occurring on a time scale that is faster than we can see it. And right now, that time scale is about 1 × 10⁻⁻15 seconds. Now, tomorrow, someone might do a new experiment that can go faster and see it hopping from one of these structures to the other. But until then, assume it's an average. So these individually are called resonant structures. And we thought that originally people wanted to think that it was resonating between one and the other, but now we think it's more an average of those 3. Now, furthermore, since these are all exactly the same structure, we just kind of randomly chose 1 bond to be the double bond and the other 2 not to be. These are called equivalent resonance structures. So what you need to be on the lookout for is whenever you have arbitrarily chosen 1 bond to be different than the others, then you have to consider all of the choices and show them and say, okay, these are equivalent resonance structures. And that's the last part of Lewis structures. All right, so I've got one more example. And so think about ozone. So ozone is O3. And so it's 3 atoms together. There's the outer oxygens are bonded only to the central one. So the skeletal structure looks like that. So hit pause and try to give me some structures for that. And remember, this was an example for resonant structures. All right, hopefully you came up with a Lewis structure that looks at least something like this. So you've got one oxygen-oxygen double bond, but you can't make two of them because at that point you'd be breaking the octet rule. And so in this case, you need to invoke the other resonance structure, which is that you've made, in this case, the right side bond is a double bond. In this case, it's the left one. So ozone has two resonance structures. Now you might be wondering why I drew this bent. And that is the subject of that is our next major topic. All right, see you then. Hopefully I will see you Monday.